So a couple of weeks ago, I went to CERN to film some videos on antimatter and the Higgs boson. And whilst I was there, I must have chatted to about 6 particle physicists for about half an hour each. And then in the end, only used something like 2 to 3 minutes max of each of those conversations in my videos. So I figured the best thing to do was just put the entire chat online so that we all can enjoy them together. So first up, here's a chat with the particle physicist Dr. Sam Harper all about the Higgs boson.
Yeah, so I mean, how do we find the Higgs boson, okay? So the Higgs boson is a bit of a challenging thing to do, and you've got to look for the right channel to look it into. One of the easiest ways to looking at it is 2 photons. Again, how we actually see a photon, because again, the thing that absolutely makes me amazed by particle physics, and I still get confused by this, okay, in all, is we have these tiny subatomic particles which go in, okay, tiny thing, and a huge detector the size of this building, and we take a picture of the event, and somehow we can reconstruct an individual photon, and 2 individual photons, and reconstruct that decay and find out there was a Higgs boson there. And I find that baffling, okay?
Yeah.
And I do this for a living.
I think everybody does, even if they don't do it for a living.
And it's amazing because what happens, we have, the photons, we have a cylindrical detector. The photons then pass through the tracker undetected because they don't have any charge. They then hit this block of transparent lead. Okay, so we grew these lead crystals about yay big. Okay, each weighing about 1.5 kilograms. And because it's made of lead, the proton then interacts into it and gets stopped by it. Because lead blocks X-rays, photons and X-ray. Okay, but we want to be able to see the light coming out of that, measuring how much goes in into it. So it has to be transparent. So we have these transparent lead crystals, we see it, and it scatters through the calorimeter, okay, all these little individual hits lighting up. And then what we do is we take those hits together, combine them together, cluster them together, and reconstruct a photon out of it, and figure out what its energy was. And we can do that with extremely high precision, like within a 1 or 2% mass resolution. And this is critical to find the Higgs.
And is that why they have to be so big, is to reconstruct all the different patterns?
So the reason they have to be so big, and this is the small one, by the way.
Okay.
It's the compact muon solenoid, is that we have to be able to measure the charged particles' momentum. And so a muon, for example, another key thing to discover the Higgs from, very low background. But the only way to measure it, you have to measure its bend in the magnetic field to measure its momentum, and the curvature basically. And it's easier, you either have to bend it more with a bigger field, and we're already at 4 Tesla, which is one of the biggest magnets we've ever produced,
wow.
okay? It's huge. I think the energy stored in that magnet can melt 18,000 tons of gold.
Wow. Okay.
So
it's a lot of gold.
Yes. So it bends in a very short distance. Atlas does a different approach, where they have a much lower magnetic field, about half the field strength, but much bigger detector to bend it across that region. And that's why they have to be so big. We have to measure the bends of these subatomic particles, which are traveling at the speed of light, more or less, okay?
Yeah. So they can go pretty far in very short bends.
Yes, exactly. So that's why they're huge. I mean, measuring a photon is actually fairly in fact, the photon bit is just, you can see the sort of blue, the tracker bit, which is the orange bit. Then there is the tiny bit after that, just about yay much long, is the photon bit that measures photons.
Okay.
Then there's the H-cal after that, and then the magnet you can see wrapped in the thing, and then there's a big muon chambers outside to measure the bend of the muons.
Nice. That's life scale as well, right?
That is life scale.
It's amazing. It's so cool. So you were here for the discovery
of
the Higgs. You've been at CERN for how long?
12 years now.
12 years.
Coming up to 12 years.
So what was it like being at CERN when there was all that buzz about it being discovered?
Okay. One of the most exciting days of my life. Okay. I mean, there was the tension of building up because there was a will they, won't they for a while. Okay. And it came very, very fast. But that day, okay, was just like, I sort of regret this now. I didn't sleep overnight on the hallways like a lot of people did.
Did they? Well, like a massive big slumber party kind of
Massive big slumber party, okay. A lot of the UK students were doing that. Huge party, waiting to get into the lecture theatre. Everything was rammed. I got in about, I think 7:30, 8:30. The entire place was buzzing, okay. Wow. Everyone was around.
Just like one massive party, I guess, which is like...
Well, the attention of CX, I mean, we all sort of knew what was going to be announced, but we didn't know the full pictures. And also we didn't know what the other team was going to say.
Oh, I see. Yeah, so what is it like at CERN, like working on one team, knowing that the other team has the same project that they're working on, the same questions that they're answering, and you could be finding different things or the same things? That must be really sort of exciting but also nerve-wracking, I guess.
Yeah, well, you want to be first. You want to do the good results. So it's a friendly competition, but also you're good friends with the other team. There's a lot of people who are married to spouses on the other experiment.
Romeo and Juliet,
yes.
CMS and Atlas.
Yes,
I love it. Star-crossed.
Lovers across across the building 40. Yes,
Detector-crossed lovers.
Yes.
I love it.
They can be from the balconies the other side waving at each other.
I love it, yeah.
And a lot of my friends are in Atlas as well, but you try and keep it professionally because the point of this is to make sure that we do right science. So if we both get the same answer independently without talking to each other, it's probably right. So it's unlikely to make the same mistakes.
That's great, yeah. Sort of like repeating your experiment, but not having to wait for the repeat almost.
Exactly. And it's also a bit terrifying because if you make a mistake and they get the discovery and you don't, it's like, I mean, you don't want to drop the ball of the most significant discovery in the last 20 years or so.
Yes, that was almost incredible, the timing that you both had the evidence that it was there and that you could at the same time announce that both of the teams had found it. Is that because it was just so clear in the data?
Well, it's because we get the same data and our detectors some of the detectors are a bit better at other things than other things, but they're roughly the same. Okay, they have different technologies and they solve problems in different ways, but they have roughly the same physics capabilities. So given the same amount of data, the same physics capabilities, we get to the same amount of data required for the analysis to discover it at the same time.
So where were you before CERN then?
So before CERN, I was at the University of Oxford studying in Chicago in the foam lab Tevatron.
Oh, okay. So you were involved with the search for Higgs at the Tevatron that was sort of the competition for CERN.
So yes, I was involved in the experiment that was searching for the Higgs there, and there was a lot of whether they would find it or not. Turns out the Higgs was in a bit of a tricky place for them to spot. So
okay, so they weren't quite designed to be able to spot it in the end, or they tried to design it, but in the end it turned out it wasn't quite right.
So where the Higgs mass right is, it's the most awkward spot we could have possibly put it in for finding it, because it's too heavy to be detected at previous experiments such as LEP, okay, but it's too light to really be easily seen at the Tevatron. Because what happens is there's a lot, because the Higgs mass way it decays most of the time to bottle quarks.
Bottle quarks.
Bottom.
I was going to say, I'd never heard of a bottle quark.
Bottom quarks, yeah. Which is the heaviest quark it can go into. And any heavier it could go, because Higgs loves mass, okay? The more massive you are, the more the Higgs loves you, and the more it decays into you. And the bottom quark is the heaviest thing which the Higgs can decay into. And so most of the time it goes to bottom quarks, 60% of the time, in fact. Unfortunately, bottom quarks, a lot of other things produce bottom quarks, particularly at colliders such as the Tevatron and the LHC, which make it very difficult, orders and orders of magnitude higher backgrounds. So it's very difficult to spot using bottom quarks.
Right, I see. So they designed it to detect much heavier particles and they weren't actually getting towards the...
They would have eventually got closer to it. In fact, they got 3 sigma, I think, at the end. Okay, so
which would be big enough to announce a discovery, but at the end of the day, you want, well, at least in astronomy, we'd be like 3 sigma, we're done. But in particle physics, you really want to drill down and make sure, right?
Yes, there was very much an announcement just before the Higgs discovery went out, saying, "Look, there's something here too, possibly." But okay, it was very much an LHC discovery.
But did the LHC and people at CERN feel the pressure from the Tevatron?
Oh yes, look, you didn't want to, especially when the LHC got delayed, because originally turned on, we had a little problem with our magnets, so it delayed us for a year, and there was Tevatron was really going, okay, we can really do this, we can find it, okay, which again added the pressure for the LHC to really get going. And everybody who had stayed on the Tevatron was like, yeah, okay, this was the right, you guys going to the LHC made the wrong decision, we'll get the Higgs.
Right, so was there a big jump in people in sort of jobs thinking, okay, the Tevatron's not going to be able to do it, quick, get to CERN so we can be involved in the discovery? Exactly,
there was a great migration around about 2006 or 7.
Across the pond.
Across the pond of all the physicists coming over, okay, it was,
yeah.
In fact, a lot of my colleagues were all at CDF or D0, so it was basically the same people would now transported to Europe.
Oh, okay, great. Was there any doubt, do you think, then, that the Higgs would have been found before that sort of 3 sigma tentative discovery by the Tevatron? Was there any doubt in people's minds that it would exist, that it the theorists seem to have been convinced for a very long time, but experimentally, were people doubtful?
So I'll let you know the secret. I was really hoping it wouldn't exist. Okay,
it wouldn't exist.
Exactly.
Why?
Because the Higgs is a wonderful and simple explanation for electric image breaking and why we've got mass. But also it means we know about the Higgs, and we've known about it since 1964. Now we found the right And it'd be so much cooler if it was something else and more exotic.
Right, so new physics. Almost like how, as astrophysicists, we're always like, Einstein was right again.
Yeah.
Like, you almost wish that there was something wrong so that we would learn something new.
Exactly. So I was also a fan of Technicolor, okay, which is
Joseph and his dream coat.
Oh yes, Technicolor Dreamcoat, okay, which is a theory which allows you to get mass by saying the Higgs is not a fundamental particle, but it's actually a composite of techniquarks. So it's like, it comes from it's like QCD, quantum chromodynamics. This is a modified version, a different analogy to this, hence the Technicolor, okay. And this being able to study this using these techni rhos, techni pions to generate the masses would have been extremely exciting because we'd had lots more particles to go on. Because we like studying new particles, and just the one we feel a little bit shortchanged by.
So did you or any of your colleagues have bets on whether the Higgs would be found then?
So I never actually had a bet per se, but I kind of was going down. I was definitely on this is not. I mean, around Christmas. So around Christmas of 2011, there was hints of something. Okay. And you've got to understand how we find particles in particle physics. We count events, and we look for excess events over a given region, usually a peak. Higgs boson forms a resonance, very clear peak. And that was, but they come and go all the time, okay? Random statistical fluctuation. This is why we have the 5 sigma burden of proof and 2 experiments. And there had been hints of like a 2 or 3 sigma thing burning in December. And it'd be like, okay, that's exciting, but in this field we've seen 2 or 3 sigma come and go many, many times, okay? So I was like, no, it's not going to happen. And there's also an excess, I think, around 170 as well, which was floating around. And everybody's like, oh, it's not there. So yeah, I was pretty confident we weren't going to find the Higgs in 2012, but I was very much wrong.
But happy to be proved wrong, I'm sure, in the end.
Exactly. I mean, it was very, very exciting to actually find it.
Joyful day for science then, yeah.
Oh yeah, I mean, the amount of celebrations that went on today, no work got done, okay? Yeah. I think the UK students, the talk was given, they came out, they had a bottle of champagne and Pimm's, okay, and just spent the day basically enjoying the sunshine and debating, like I'm relaxing in the newfound Higgs boson.
Yeah, I think everyone deserves that break though after so many years worth of effort to get to that point, and so many people must have been involved as well. Like the atmosphere on, campus basically we can call this, right? Must have been fantastic.
It was intense, yes, and like I mean I think each paper, the 2 papers on this collaborations had 3,000 authors on them.
Wow.
To give the historical contribution over many years that many people have made in this collaboration. Many people have made to this collaboration.
Wow, 3,000 people. I wonder if the Champagne region in France noticed a dip that year in stockpiled bottles.
Oh, we did get bottles of Higgs boson champagne made for a celebration.
Nice, that's so cool. I love that. So the famous plot is obviously that trace of energies, and you can see that peak at 125 GeV of that's the Higgs boson. But obviously with 3,000 people sort of working towards it, I know that obviously a lot of other stuff will have gone on. So like, what was your contribution to that day or to that plot? Or were you sort of working on more like the bigger picture side of things? Or like, what was your specific contribution? So
my expertise is actually in triggering and electromagnetic objects. So this is very important to the Higgs because, well, without triggering, you don't get the Higgs. So what happens is we collide 40 million times a second. Wow. And we can keep about 1,000 of those. And we have to keep the right 1,000, because if we don't keep it, it's gone. So you don't want to throw away the Higgs boson accidentally away just because you didn't write the right trigger. So a lot of my contribution is developing the trigger algorithms for electrons and photons, which are actually one of the key things for discovering the Higgs. The Higgs was discovered mainly for the 2-photon channel and also the 4-lepton channel in Higgs to ZZ. And electrons being a huge part of that, and photons. So without those algorithms, it would be much harder to find the Higgs.
So why was the LHC crucial in the end to finding the Higgs? Like, what set it apart from the other detectors that made it able to detect that signal?
Well, the LHC just has energy. It has the Tevatron only has 2 TeV of energy. Well, the LHC has 7 and 8 TeV, and now has 13. So it can pump more energy into that collision and produce the heavy Higgs boson. Because the 125 GeV is a very heavy particle to produce. So it takes a lot of energy to kind of give it a good oomph to get it. So the Tevatron just didn't have quite enough juice to really get enough Higgs.
Right.
The way we celebrated was we had a Higgs BBQ, okay, with the invite.
That's my favourite pun ever.
Yes. And this is how we celebrated Higgs Dependence Day.
No, I spoke too soon. Higgs Dependence Day is my favourite pun ever.
Yes. So as we have a little Higgs BBQ on Higgs Dependence Day, and the invites were all written in Comic Sans. And if you look at the talk that was announcing it from Fabioli, our Director General now, but at the time Atlas spokesperson, you'll understand why. So, I mean, one of the most important scientific discoveries of all time was communicated to the world via Comic Sans.
Yeah. We look back and we recognise errors made in the previous decade, I guess.
Had an interesting colour scheme too, okay? But shows that it's scientific content that matters, not the presentation.
Yeah, exactly. I mean, obviously that was back in 2012, but CERN hasn't shut down since then to be like, right, done and dusted, that's everything. So what are the questions that are being asked now by you and the team here in terms of the Higgs still? Like, we obviously don't know all there is to know yet, so what do we still not know?
Well, we want to know that it is the Higgs boson and has the properties of the Higgs boson. Now, back in 2012 when we discovered it, you notice the paper does not say it's the Higgs boson. No mention of the Higgs is not the Higgs boson. Because nobody knew it was the Higgs boson at the time. We just knew there was a new scalar particle which had spin not equal to 1.
Okay.
And that was the discovery. But it kind of looked like the Higgs boson, quacked like the Higgs boson, so we were kind of quite excited.
Okay, so in writing it never says it, but in the press conference it was like, this is the Higgs boson.
Yeah. Peter Higgs is there, okay, yes.
Yeah.
But
it's his particle.
There's a difference between, well, the scientific standard is much higher to say, because I mean, it really was very clearly the Higgs boson, but scientifically we hadn't proved it.
Right.
So the first thing we had to do is we had to figure out that it was the Higgs boson, and measuring how it decays to different particles. Because the Higgs boson the decays are completely fixed. It's very well predicted how exactly it'll behave. It's completely, the theory is very good. So we had to measure it, check that it was a spin 0 particle, that it decayed in the right things. And it took us to 2013. Okay, actually, I was in the conference where we decided it was a Higgs boson at this point.
Okay.
It was not the Higgs boson at this point, but it was a Higgs boson. It made the criteria for Higgs boson. And then we've been looking at trying to actually measure the decay to other channels. Because just because it decays, so the Higgs boson gives mass to vector bosons, the W and Z, and it also gives mass to fermions. So like electrons, muons, quarks. And it took a while to actually see it decaying to fermions. And we weren't sure if this was a Higgs boson this was a Higgs boson that only gave it to electroweak symmetry, and there was another Higgs boson that generated for fermions until we actually saw it decay. And in fact, it took us a little while to see it. There was evidence in Tau Tau and BBB, but it took a while to see it. And I think 2018 is when we actually first saw it going to bottom quarks. Which again is 60% of the decays, but it's so hard. They're so hard to find. So again, showing that we actually can measure at that point, it was very clear that it was now the Higgs boson, and we're still trying to measure all the other branching properties of it, seeing it, checking all the decays that they match up the standard model. And the reason for this is the Higgs boson is the wonderful portal to new physics. So, I mean, particle physics is doing all right. We've got this wonderful model, but we've so far explained 4% of the observable universe. And
us astronomers are like, we're waiting, guys.
Yeah, exactly. So there's room for improvement, and we're also missing a fundamental force, gravity. So there's work to do. Okay, the standard model is not complete. So we think there's new physics out there, and WIMPs, dark matter candidates. We think there's a heavy particle out there which is forming what we call as dark matter, which we see in gravitational effects. Dark matter obviously has mass. Higgs boson generates mass. Higgs boson should like dark matter. This is so now we know exactly where to look for the Higgs boson. We can start seeing is it decaying to something? Is it decaying to dark matter?
Wow, that'd be really cool.
And but this is quite challenging because we can't see dark matter.
Yeah.
So it's Higgs to invisible.
Yeah, so it's like the missing stuff in sort of the conversation.
Yeah, the collision.
It's the missing stuff in the conservation of the energy or the momentum of some point in the decay where you're like, where did that go? We have no idea where that went.
Exactly.
Maybe it's dark matter.
Exactly.
I never thought of that. That's so cool.
And that's one of the things that the Higgs. That's why the Higgs is we really want to measure all these properties because it's sensitive to new physics, and we really and so it's a perfect portal. Also, there's Hidden Valley models where we think there's another set of long-lived particles which we don't interact with a normal standard model, but again could couple via the Higgs to us. So the Higgs is a wonderful portal for new physics.
So there's so many questions still left to ask, I guess.
Exactly, and we really want to understand. Again, we haven't. One of the decay modes we really want to look at is Z gamma. In fact, I'm reviewing the analysis for that in CMS right now, and again showing it does the Higgs boson decay to that in the correct way. We want to measure its mass to higher precision. We want to see its width, because the width is important. If we can measure, the width is quite challenging to measure.
The width of the peak?
The width of the peak. And the problem is the Higgs boson is extremely narrow, and we can't measure it that well. But, under putting constraints on that, means we can, the width is related to the total amount of decays. And if it's larger than expected, it means it's decaying to something else we don't know about. So that's another way. That's difficult to do. And then also we want to measure how the Higgs couples to itself, and there's all these exciting new physics things we can play around with it. So it's our toy, okay?
Yeah.
And so this is why there's talk about building a linear collider, which can produce a lot of Higgs. We can really study it and see what's. Because again, it's a new particle. We want to know everything about it. Okay?
Yeah, exactly. I like the fact that you can just tweak it and see what changes, and see if you can almost break your model that you've made by tweaking something to, try and figure out what we don't know still. It's really cool.
Exactly. We really want to find new physics and break everything. We really want to test everything. And also the other things, we wanted to measure it to top quarks. And that's a challenge because the Higgs actually is less than the top quark. It needs to have twice the amount of mass as a top quark to decay into it. It's only got 125 GeV compared to 175 GeV. So what you have to do is you have to produce it via top quark couplings, okay? So, and it's a very rare process, the LHC. But again, in 2018, we actually managed to measure that and actually directly probe that and measure its couplings to top quarks, which turn out to be compatible with the standard model, sadly, but still, it was fun.
So when does the new switch on of the upgraded LHC take place? When are you going to be able to get your hands on all of the buttons and everything to do all your tweaks?
So the thing what we need is we need data. We need number of Higgses. So the Higgs decays, these decays we're looking at are rare, and we need a lot of Higgs for it. And luckily we've got the high luminosity LHC, which is our next thing coming up, 2027, okay, I think, although the schedule is changing.
Yeah.
So coming up in a few years. And right now we're preparing for that right now. Because it's the LHC right now is still actually early in its program. We've taken 5% of the data we plan to take of the LHC program.
Wow.
So we have a lot coming.
Yeah, and I bet you've already got like absolute stacks worth of web servers somewhere hosting all the data, right? That you've already taken.
Oh yes,
so.
I think it's like 30 petabytes a year or something.
Wow.
Comes out of this machine.
Yeah. So you've already overtaken the sort of energies of particles you're producing in bytes worth of data.
Oh yeah. We store a lot of data. Okay.
Yeah. So obviously you mentioned that the Higgs is this probe for new physics, but the gravity still isn't in the standard model. So when I hear like, the Higgs gives something mass, I think of general relativity. And I think about that theory of gravity in terms of, mass warp space-time. Is one of the future goals to understand like how those two processes might couple and like whether one can explain the other, and can we come up with this sort of unified theory of both? Or is that like so far in the future, do you think?
Having gravity and unified in the standard model would be wonderful, okay? And this is extremely challenging. Gravity is super weak. Yeah. It's super weak. In fact, we can't detect it in our experiments at all. It has literally we completely ignore it. It's orders and orders and orders of magnitude smaller than the other forces. I mean, the Planck scale is 10 to the 19 GeV, while the electric weak scale is a couple hundred GeV.
Yeah.
So huge difference. But one thing that actually wish I do, I'm a bit of a gravity fan. Okay. And
you both.
Okay. And and this is not particularly Higgs that can relate into this. Is why I look for extra dimensions as well as one of my side things in the past as well. So I've done a lot. And one of the reasons why we think gravity is weak and how why it's weak is it actually gets diluted across extra dimensions. The volume of space that gravity goes out into is actually huge. We can only see a small fraction of it, and that is really that's a lot where the research is going for gravity. And of course, gravitons can have a mass, and through the excitations of the extra dimensions, it's kind of a cool topic.
That would be really cool, yeah. I just wonder how like many paths that could take us down, of understanding maybe what even like matter turns into when it is a black hole or something, what actually matter looks like in terms of it still has mass. The Higgs obviously gives it mass, but what is it? And that will come from, I think, linking the two.
Well, the Higgs gives mass because it has a non-zero field excitation. Of course, in the early universe, everything was massless. Because if you have enough energy, the symmetry is restored, and the Higgs field is because the Higgs field is a weird field in the sense that it gains strength as when it's not. It's easier for it to have a non-zero value. Its lowest energy state is having a non-zero value. As opposed to other fields where the lowest energy state is having a zero value, and that's how but once you're above that, you actually all massless. And the early fractional early of the universe.
What are we talking, like 10 to the minus?
10 to the
like
minus
20
seconds or something.
Yeah.
Yes, yeah, exactly. Is everything, so that can be massless then. And it's when the universe cools down to the scales we currently are at, I think it's 120 GeV or something when it hit. Then everything starts generating masses.
It's so weird. It's one of those things like you can't quite picture the fact that like Higgs bosons are giving us mass like right
Exactly.
now. You know.
Well, it's not giving us, our mass does not come from the Higgs boson.
Okay, that's not what I understood, but yeah, please
And
explain.
okay, so this is a common misunderstanding.
Yeah.
So it gives the mass to the fundamental particles. We're not fundamental. We're made of atoms.
Okay.
And all the energy in that is actually quantum cryodynamics binding energy. Is the interaction strength, the gluons exchanging. All that is what gives us mass. The proton mass is 1 GeV. The quark masses are much lower than that. They don't even, they're a negligible fraction of it. So all the Higgs does is stops us going off at the speed of light from each other.
Oh, okay. So the Higgs boson gives the quarks mass.
Yes.
But then what gives a proton mass is the forces holding those quarks together.
Yes.
Okay, right. I see.
And that's actually...
I've never understood that, I don't think.
Yeah, if you look at the quark masses, it's actually, if you add the three of them together, it doesn't come anywhere near the proton mass. So the vast majority of our mass is nothing to do with the Higgs boson.
Yeah.
But if it wasn't for the Higgs boson, all of individual quarks and electrons and that stuff would be flying away from each other at the speed of light and wouldn't be able to bind together. So we only exist because of the Higgs boson, but the majority of our mass comes through the interaction of quantum chromodynamics.
So is that where the phrase God particle came from? Because we only exist because of the Higgs boson?
No. I mean,
I know that's a phrase that particle physicists don't really like. Is it the God particle?
yes. I mean, it was supposed. Leon Lederman coined it, director of Fermilab, and it's known as the goddamn particle is what he wanted to do because it's the most frustrating thing in the world because it was so difficult to find. It was right in. So the place where it is really nice because you can measure all its couplings because it decays to a lot of things very easily, but it's in the worst possible spot to find. Okay, I mean, like, if it'd been any heavier, we'd have found it earlier on because it can decay to Z boson, to pairs of Z bosons, W bosons, top quarks, very easy. But where it is, it's just decaying to bottom quarks, which are very difficult. And if it was any lighter, LEP would have seen it, which has LEP is a much cleaner environment. All the energy goes into the collision, has no extra hadronic jets from the rest of the proton because it's just 2 electrons. So we would have actually seen it very easily at LEP. But LEP got to 115 GeV. And it was 10 GeV short.
God,
just
it's so annoying. It's like Sod's law, isn't it? That it had to be like the
Yeah.
reason we exist just had to be in the annoying place.
I mean, I think there's a lot of LEP physicists who are a bit annoyed that there was 10%. They spent a lot of time looking for it, and there was 10% away, and then we had to spend another 10 years or so building the LHC to actually find it.